Let us see associative mapping. In associative mapping, the simple rule is any main memory block can go to any cache block. Okay, such a way we plan. So that what happens, so that we will be effectively utilizing the cache. But what are the consequences we will see. First we'll see with one example. Let's say you have 4 cache blocks 0, 1, 2, 3 and 8 main memory blocks as usual. Then these are the and assume that let's say each block has 2 words, and I am assuming that my memory is word addressable at this moment, okay, so that it will be easy for me to explain you the things. So we can extend it to byte addressable also, not a problem. First think about word addressable systems. Now there are 16 words, right? Because each block has 2 words, then 16 words are represented by 16 binary addresses 0000 to 4 ones. Now these two represent block number 0 in that way. So this block 0 is identified by last 3 positions. You see 001 means block 1, this is block 2, block 3, in that way. So last 3 positions identify the corresponding block number. Now there is no mapping. Now I can say anything can go to anything, right? That's why there is no cache index. So generally in direct mapping we had 3 divisions, right? One is word offset, after that immediately we had cache offset or cache index. It depends on the number of cache blocks. This time we are not mapping one particular block to one particular block, then no cache index, directly everything is tagged. What are we going to do? I will tell you. Example, let's say currently you have decided to keep this block number 0 of the main memory somewhere. Then what we do is we just go to randomly some memory locations. Example, I fix this cache block 0. I write W1, W2. That means currently this block 0 of the main memory is available in the cache. Okay. Now immediately there will be of course valid bit. I don't show the valid bit here for easy understanding. Let's only use tag field. Okay. So how many bits will be there in the tag field is 3 bits. That will be 0, 0, 0. Now you see. So 0, 0, 0 block of the main memory is now in this cache. So that's easy, right? Now example, whenever you keep this data, this block, you know one thing, right? Always in the cache we keep a block rather than a particular word. Though you want to keep this particular word in the cache, then we keep total set, right? Example, let's say you want to keep W11, W12, then what is that block number? 5. So that means 1010, 1011. We keep that W11, W2 anywhere, not a problem, which should be free. Then what should be the tag field? The tag field this time should be 101. This entire remaining thing is tag field. Now example, let's say I am searching. How I search, you see, suddenly you thought of accessing the memory. Okay, now this is your random memory address 1010, 4 bits. Okay, now this is your processor. How processor is going to access the memory? You see, first it will check the cache. In the direct mapping technique, what we did, we divided into 3 parts, like this and like this. I said this is cache offset, and we thought, and that is a rule of course, in direct mapping technique, if and all if this word is located, that will be in the cache block of 01, cache of 01th block. That means one block number 1. But here there is nothing like that, so it can go anywhere. There is no cache offset. Directly we will take 101, right? Now we'll search every tag, because see, this memory word can go anywhere. If it is anywhere means any cache block, we don't know, then we have to search. That's why use this tag 101, search here. 000, no. 101, yes. That means what? Definitely 1010 is present in the cache. If you have a doubt, you check it out. What is 1010? 1010 is nothing but W11. Yes, W11 is available. Sir, we have a question. What is that? Somehow you identified the block, right? In that there are 2 words. How do you know that this is W1 or W11 or W12? We have this bit, right? What we do is this entire cache block will be taken. Okay. Now we selected this block. Since this bit is 0, then this word will be selected. Such a way we design our circuit. Understand? So this will decide that. Understand? Now one more example. Example, let's say, so this memory word, okay, 1110. So your processor has decided to search for a memory word. That means it wants to fetch a memory word called 110, 1110. So first we check here, tag 000, it's not 111, right? These 3 bits. So here 101, it is not 111. That means miss. So we say cache miss because that data is not available in that way. So associative mapping will work. But if you see the problem, so did you remember in the direct mapping technique we used only one comparator. So here also if you use one comparator, then what happens we'll see. First, if you use only one comparator, then we have to compare this with your tag, original tag. Okay, this is your, let's say, real address. Okay, this is your tag. We have to connect this tag bits to this comparator and we have to compare. Then if you get miss, that means if the output is 0, then we have to connect second tag to here, then again we have to do. But you know, it takes lot of time. If you have, let's say, 100 blocks in the cache, generally the number of blocks will be 2 to the power of x. Okay, it will not be 100. Let us assume 128 blocks. If your cache has 128 blocks, the number of tag fields will be 128 because every block will have tag. Then if you check linearly one by one, then 128 times we have to check. That takes lot of time. Each comparison takes one cycle, let's say one clock cycle. 128 such kind of tag comparisons takes 128 cycles. Then what is the purpose or benefit of using cache? Correct? So we should do parallelly. That means, you know, we have to compare this with this, this with this. That means, see, tag, let us say this is tag 1, this is tag 2, this is tag 3, so on. Tag 1 tag, tag 2 tag, tag 3 tag, everything should be compared parallelly. For that, one comparator is not sufficient. So we will be having a dedicated comparator for everything like this. Okay. Now you see. Similarly, here one comparator like this. So now one comparator here like this. In that way, so this tag is connected to every comparator at a time and checked parallelly. So one of them, if at least one of them will hit, we'll use OR gate. So you get results, right? Result number 1, this is result number 2, right? Comparator result. In that way, all that comparator results will be connected to OR gate. So what happens eventually, really data is available. One of the tag comparator will give you output 1. In the OR gate, one of the output is 1, then you get 1. That means hit. If output of R is 0, that means, you know, no tag matches, then output is 0. Then with one comparator time, we can do it. Understand? But the problem, unfortunately, so you need lot of comparators, then, you know, it will be costly, right? Hardware will become very costly, right? Cost is very much. Direct map technique, in that only one tag comparator is required, then that will be the cheaper circuit, right? It's a trade-off. But the direct map technique doesn't have flexibility, right? So that means what? You will be getting lot of cache misses. Why you will get lot of cache misses? Recall, already in the cache block someone is staying now, another one wants to come to same location, but there is a space, but because of the direct mapping technique, that second fellow also wants to go here only because his formula says that we have to go here. Then you will not be utilizing the cache properly, then the number of cache misses might be more, right? So that will affect the again CPU performance. So finally, that is the difference between associative mapping and direct mapping. Okay, we'll see the differences again. First thing, that is circuit wise, so that is cheaper circuit, right? Direct mapping. So associative mapping requires lot of hardware, lot of comparators, number of comparators required equal to number of cache blocks. That is one thing you should remember. Second thing, so that's why, you know, hardware is very costly, right? That you should remember. Now direct mapping and associative mapping, if you see, associative mapping is flexible. You can keep any data anywhere, so that, you know, number of cache misses will be reduced. We'll see with some examples. We'll take one example and we'll see number of cache misses in direct mapping and associative mapping. After that, at that time you will realize why associative mapping generally requires will have less number of cache misses. Very simple. Because example, there is no space here, we can keep here. If there is no space, we can keep here. We are effectively utilizing the cache. But in the direct mapping, you are not doing that. So we'll see with one example. So here, so example, let's say you have 4 cache blocks. 0, 1, 2, 3. Okay, and let's say main memory contains 256 blocks. Okay, now they are, you know, that 0 to 255. Now the memory references are, let's say, 7, 11. These are all block numbers. Okay, main memory block numbers. The current memory references we are getting are 7, 11. Let's say after that, let's say 13, then later 7, then, you know, maybe 7, 11, 13, 7. After that, let's say again 11, again 7, again 11. So what will happen, we'll see the number of cache misses we will see in the direct map technique. Okay, let us apply direct map technique. In direct map technique, what are we going to do? Initially, we will be keeping 7 where? Recall. See, I will tell you one shortcut. Whenever you know the main memory block number in decimal, if you want to know the cache block number where it goes, simply divide that 7 by, you know, that number of cache blocks. Okay, and get the remainder. What is the remainder here? 3, right? So that 3 is going to be the corresponding cache block. That's it. So 7 always goes here. Now 11. So that 11, simply divide by 4. The remainder is 3, right? So it will go to same place. But already it is occupied, right? Then we have to keep 11 here. Okay. That will be the right strategy, because, you know, most recently used one is 11, right? Correct? That's why we have to keep here. So this is called a technique called, you know, least LRU algorithm. Here, whenever you have to replace any data item, whenever, because, sir, why we have to replace? Already I told you, the major principle of cache is whenever data is not available in the cache, we have to transfer the data to the cache, then we access, correct? So that always we keep the recent fresh data, right, which is most relevant, otherwise most frequently accessed. That's why, so here currently people are accessing 11, then we keep 11, right, 11th block, so that we get the benefit of spatial locality, right? Now after that 13 comes. If 13 comes, then what to do? So far how many cache misses? 7, let me mark it, cache miss. 11, cache miss. Now 13, divide 13 by 4, you get remainder. 13 means 1, right? So this is free, we can keep here. Then after that 7. Now again cache miss, correct? So whenever 7 comes cache miss, then 7 goes here, then we have to remove 11. We don't have option, right? So that way. Then, sir, why don't you keep in this place? In the direct mapping technique, always 7 should go there only, so that we can avoid the search, right? Now 11. Again there is a miss, right? We keep here. So now 11 is here. After that 7, again miss. Though you have space, you are not utilizing it, but you are, you know, getting lot of misses in that way. So since 7 and 11 wants to go to same location, then every time you get miss. Miss, after that, you know, miss, because first time we are keeping, right? After that 7, miss, 11 miss, 7 miss, 11 miss. In that way, everything is miss. Then that's a worst behavior. If it is associative mapping, what is going to happen, we'll see. So no division, nothing. Anyone can go anywhere. So 7 can be kept anywhere. Assume that, let's say we are keeping 7 here. Okay. Now 11, anywhere you can keep here. Then 13, keep here. So 7, keep, so here already it is there. Then hit, right? Now I can say 7. First time when you access 7, miss. Second time, next time when you access 11, miss. 13, miss. But next time when you access 7, it is available. So hit. 11 again hit, 7 hit, 11 hit. So number of misses are only first 3. Understand? In that way, associative memory will associative mapping will have, you know, definitely advantage over direct mapping, but hardware wise it's, you know, costly generally. That's why people don't use associative mapping. Similarly, people don't directly prefer direct mapping. So there is one more alternative we can go for, that is set associative mapping. We'll see that set associative mapping also. After that we'll decide which one to use. Okay, so it depends on this, you know, designers, like what to use. Just understand pros and cons. After that we can fix it. It depends on our requirement. So we have 3 models: direct mapping, associative mapping, set associative mapping. Set associative mapping is a compromise between direct mapping and associative mapping. It will have, you know, both of the features. Like, what is the main feature of direct mapping? Less hardware, right? What is the advantage of associative mapping? Flexibility, correct? So that cache hit ratio will be improved, right? Now we'll see set associative mapping. In set associative mapping, we will be dividing our cache blocks into sets. Okay, example, in this one I have divided into two sets. Okay, now what are we going to do is we will be fixing, example, any main memory block. Let us take B5. So this block number 5, where it goes is decided by the set number. That means either it will go to set 0 or set 1, that is fixed, like direct mapping. Okay, in direct mapping each main memory block will go to fixed cache block, right? But here in set associative mapping each main memory block will go to a fixed set. Okay, maybe it is set 0 or set 1. How I decide is, so I simply divide, because I have two sets, right? Then I take the block number of main memory, block number. So I divide that block number by 2, because number of sets are 2. Example, let's say B0, block number 0, right? So 0 will go to set 0. That means in set 0, the candidates for set 0 I will tell you 0, block 0, then 1. When you divide 1 by 2, then what is the remainder? Remainder 1, right? That's why it will go to set 1. In that way, some logic, that's it, correct? Because we have two sets, then if you divide any main memory block by 2, then the remainders will be 0 or 1. Then properly we can map them to set 0, set 1, that's it. So all the remainder zeros will come here, remainder 1 will come here. So that 0 and 2, then 4, then main memory block 8. I am assuming that we have 16 blocks, then 8, main memory block 10, 12, 14 will come here, and in set 1, main memory block 1, 3, 5, 7, 9, 13, 15 will come here. Understand? Okay. Now, so 0th main memory block always will come to set 0. But in set 0 you have 4 blocks, right? Where it will go? That is again flexible, like associative mapping. Now, particular set, in this particular set, we follow the associative mapping. That means, so 0 may sit here or sit here, anywhere you can keep if the space is free. Okay. If this space is not free, then we'll keep here. If this block is not free, then we'll keep here in that way. Understand? Then that mapping is called set associative mapping. Now, how you play with binary patterns, we'll see. So, in this binary pattern, if you see, the last digit, if you see, that will be for word number, correct? Because we have 2 words in every block, then this bit is dedicated for what? Word offset. Now we have 4 digits, right? 4 digits. So these 4 digits, if you see, for these two, first block, these 4 digits are showing 0, 0, 0, 0, 0, 0, 0, 0. That's why it is block number 0. In that way, easily we can, in our imagination, block number 1, but binary pattern for that memory address is 0, 0, 0, 1. In that way, we can map these two things. For us, it is block number 1, this one. What is the binary pattern for that? Last 4 bits are 0, 0, 0, 1, 0, 0, 0, 1. So finally, my binary pattern, or which is memory address. So what should be the size of memory address to have this kind of structure? How many memory blocks you have? 16, right? 0 to 15, 16. Each block contains how many words? 2, 32 words. Assume that, let's say, your main memory is word addressable. If it is word addressable, then how many addresses are required? 32. To represent 32 addresses, how many bits are required? 5 bits. In that way, so 5 bits will be decided. Now 1 bit is gone for word offset, then remaining 4 bits. So these remaining 4 bits will tell that the number of main memory. That means main memory block number. Always you remember, it's not only for set associative mapping. Generally, so these bits other than word offset will be representing main memory block number. Now what do you want? You want to know which set number it goes, right? How you decided? You divided block number by 2, right? What is that, the significance of 2? Because we have 2 sets. What if we have 4 sets? Then we would have divided that by 4. Dividing a main memory block number by 4 and getting some remainder is equivalent to here taking these bits from right to left. Both are same. Okay. Example, you see, this is 0, 0, 0, 0, main memory block number 0, right? If you see this first bit, that indicates the remainder if you divided that number by 2, right? If you divide block number 0 by 2, what is the remainder? 0. Definitely this one. Let us cross check with another one. See this one. This is a block number 0001. For block number 0001, main memory block number, this bit indicates that it is 1. Then if you divide this block number, which is nothing but block number 1, by 2, then what is the remainder? 1. This will be indicated by that. Okay. Now let us try to understand with 4 sets. Example, if you have 4 sets, okay, they are set 0, set 1, set 2, set 3. If you want to know which main memory block number will go to which set, then simple technique is what? Divide the memory block number by 4. Example, let's say you have a main memory block number 7, okay, then it should go where? If you want to know, take the main memory block number, divide by number of sets. Number of sets are 4. Then what is the remainder? 3. Then this main memory address 7, main memory block number 7 should go to set number 3. Then how to do the same thing, how to assert the same thing with memory binary patterns, I will tell you. Write 7 in binary pattern 0, 1, because see, I am assuming this number of bits, 5 bits, right? 0, 1, 1, 1. This is for, leave this one because this is word offset. Okay. Now we have remaining 4 bits. 7 main memory block number means 0, 111, right? This is main memory block number 7. Now focus on these two. Is it not remainder? You see directly 3. That's why these 2 digits are going to represent set of set, right? Which set it should go will be decided by the next bits. From now onwards, remember one thing, in set associative mapping, we divide our main memory address into 3 parts. The first part is word offset, understand? Now second part is set offset, that will decide which set this block should go. Now these remaining bits are tag bits, okay? These tag bits we know the usage of tag bits, right? Already we have seen, okay? Now example, how to map a particular main memory address I will show you. Example, you have one main memory address, let us take B12, okay? Let me take B12. In B12, entire this block number 12. What is the binary pattern for that block number 12? Block number 12 means 5 bits, right? 1, 2, 3, 4, 5. We know that these 4 bits represents block number. So write binary pattern for 12. This is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. 2 power 4 should be 0, 2 cube will be 8, 2 power 2 will be 4, right? 8 plus 4, 12. See, now this is for word offset, ignore it. So I am just talking about main memory block number. This is your main memory block number 0110. Where it should go? Because there are 2 sets, simply take this bit, right? 0. So that's why keep it in set number 0. In set number 0, where you keep this data, this block data? Anywhere, because there are 4 blocks, right? Anywhere you can keep, right? Wherever you keep. Example, if you keep in this second block, try to understand. If you keep in this second block, then there will be tag, okay? I am showing the tag here. This is second block. So example, you are keeping the data of B12, right? This entire block B12. Let us say this data is D. Keep the data D, okay, here. What is the tag for that data? I will show you. What is the tag? What is the tag? These 3 bits, 0, 1, 1. You keep 0, 1, 1 here. So searching will be easy. Now how to retrieve the data I will show you from the cache. First, your main memory address will be taken again, and word offset will be ignored first of all, because we are just searching for the block. Then this 0, 1, 1, 0 will be looked. Then this 0 will index to the right set. This is set index, okay? So using 0 you will index into the right set, okay? Then this 0 will index you to this set. Then you will come to this group of 4 blocks, but among them which one is right? Then what we do is we compare every tag with our tag. What is our tag? 011, right? Mr. Tag, are you 011? No. Mr. Tag, are you 011? No. Mr. Tag, are you 011? Yes. Then definitely this is our data. In that way, so search will be done. In that way we will look into the cache. Understand? So this will be definitely in between direct mapping technique and associative mapping. We are not searching all the blocks, right? We are not searching all the blocks, and we are searching 4 blocks. It's not direct mapping. In direct mapping we'll search only 1 block. So it is in between direct mapping and associative. Now set associative requires how many comparators? Because we have to do comparison parallelly, otherwise it takes lot of time, correct? So that's why definitely we have to plan our hardware such a way that the searching process should done parallelly. That means we know that once what we do, I will tell you. First of all, we index into this right set. Once we go to right set, then we will connect this tag, this tag, this tag, this tag to 4 comparators. That means we use 4 comparators, one here, one here, one here, one here. So the other input of this comparators is our tag bits. Okay. So parallelly all the comparators will be compared, and one of them will give the hit, right? Whenever one of the bit gives hit, then we can directly take the data from that appropriate bit. Understand? So this is the way things will work. Now we have one question here. Sir, yeah, somehow your one of the tag will hit, right? Comparator will give the output 1. But how do you know that a particular comparator gives 1? For that, generally what we will do is we will use multiplexer. Okay, so this multiplexer will decide that. Okay, what we do is the result whatever you get, right, the tag results. Okay, so example, let's say this tag result is 0, this tag result is 0, then this tag result is, let's say, 1, right? This another tag result is 0. Then what we do is we connect these results 0 0 1 0 to this multiplexer. Let's say if I do that, okay, then this multiplexer is going to select one of the blocks among these 4 blocks based on these 4 results. We can plan it, not a problem. Understand? So what we do is this multiplexer will be connected to the results of the comparators. Okay, so if the result is 0 0 1 0, then we can say that, then we can select the right block. That which block? Third block. If the result is 0 0 0 1, then we will somehow select fourth block. If the result is 1 0 0 0, then we'll select the first block in the appropriate set. In that way we can plan. Okay, don't worry about that hardware part. Understand? So this is about set associative mapping. Understand? Now the number of comparators, if you want to know, exactly equivalent to number of blocks in the set, right? Now number of comparators in associative mapping is total number of cache blocks, right? Everything we have to search. Number of comparators required in your direct mapping is only 1, right? So that is the difference between number of comparators in direct and associative and set associative. One more thing. So one more question they ask in the GATE exam. They ask number of bits required in tag comparator. So we are going to have a comparator, right? That comparator is going to compare 2 inputs, right? What is the size of the input they compare? That is called size of the comparator. What is the size of the comparator? It depends. Example here, that comparator is comparing how many bits? Tag bits. That's why that will be decided by number of tag bits. Simply compute the number of tag bits. That number of tag bits are going to decide the size of the comparator. So simple. Understand?